So I asked a student of mine who is working on computational electromagnetics to simulate two kinds of problems. The first problem is in the optical range, and the second problem is in the microwave range. So for example, in the optical range, what we are interested is a kind of a dielectric mirror, which is basically constructed using slabs of glass and with different permittivity and permeability. So in fact, we are stacking them in order to create a kind of a dielectric mirroring effect. So what we are going to see here is a physical phenomena where the light coming is getting reflected from different layers, and we are trying to model this problem using the finite difference method to see what is the real physical phenomena and how does the numerical method capture that real phenomena. There are possibilities to model this problem using various methods. Right now we are going to focus on a very simple basic method which we have covered, which is the finite difference method. So we will simulate this problem and see how the discretization can be varied and what is the impact of discretization and how the physics can be replicated in a virtual model. So that will be one of the first examples that we will be looking at this lab tour. And following this, I've also asked him to simulate microwave example for a waveguide in the X band. So to see how does the microwave waveguide is being modeled in a virtual environment using finite difference method, and how we can see the impact of the radius of curvature or the bend of a waveguide is being replicated and how the physics is represented in the virtual platform. So that's what we are going to see in this lab tour. So let's go and see what the student has got for us. So Mayur, yes, you've been working on two problems using the finite difference method. So could you please explain us about this Bragg's reflector?
So in the first example, we are modeling a Bragg's reflector. It is nothing but a dielectric mirror.
Yeah.
So dielectric mirror means it reflects the incident energy. So with whichever incident beam is coming, so part of it will reflect, and this is required for applications wherein we need or beam to be reflected between some points.
Layers. Yeah, yes. Okay. So basically what we are doing is we are staggering slabs of different dielectric constants, and kind of we are trying to stack them up. So yes, the light is going to come and it's going to reflect it. So let's go into the physical modeling, how we have done it.
Yes. So this is the model which I can show the diagram of that model.
Okay.
So in this basically we are taking two different layers with different permittivity values.
Okay.
And we are stacking them periodically.
Okay.
So as you can see, first layer which is marked in a different color as compared to second layer.
Okay. So the red one is having a permittivity or relative permittivity of 2, and then the white one is having the relative permittivity of 4, just for example.
Yeah.
And then the thickness of them is 0.25 micrometer.
Yes. And the wavelength which we are using for this particular simulation is 0.5 micrometer.
Okay, so it's a 0.5 micrometer range. So
and if we try to understand the physics behind it, it is dependent on a wave is coming from one medium with one particular permittivity, and it is going to some other medium with different permittivity. So it is seeing an abrupt change. So it will undergo reflection. Some part of the power will undergo reflection, and the other will be transmitted.
Okay. So basically these are the two factors here. You have a gamma and then T, which is gamma is the reflection coefficient, and this is the transmission coefficient. And you're modeling them using this. So N1 and N2 are
index of the first medium.
So these are the refractive index of the different mediums.
Yes.
So N1 is for the first medium and N2 is for the second medium.
Second medium.
So let's go forward.
Let us go to the example which I have simulated.
Okay.
So basically, this is basically the same problem. I have done it using 3 different discretizations.
Okay.
So first discretization is wavelength by 10. So lambda by 10 discretization in space. And second one is lambda by 5.
Okay.
And third one is lambda by 3.
So basically what you're saying is there are you have done the same problem for 3 different cases.
Yes.
The first case you have 10 cells sitting in the per wavelength of the incoming light, and for the second case it's 5 cells per wavelength, and then the third one will be 3 cells per wavelength.
Yes.
Okay.
Yes. And we will be looking at the 2D simulation of that.
Okay.
And we'll see the window.
So you have kind of translated the 3D problem into a 2D problem, and then you're trying to simulate it.
Yes.
Okay. So show us first the 3 lambdas per wavelength.
Okay.
So
yeah, this simulation is for lambda by 3 discretization.
Okay.
So I'll start with.
So the incoming direction, the light is coming in this direction.
Is coming from this direction, and
we're
recording transmittance here.
Okay.
And we'll be recording reflectance at the back of the source.
Okay. So basically, what you have is you have different slabs here, and you have a sensor to measure the reflected beam, and then you have a sensor here to measure the transmitted
power.
beam.
Yeah.
Okay.
So I'll start now simulation. So we can see that the incoming wave is getting reflected from the first layer itself.
There is nothing going inside.
There is nothing going inside, so almost transmittance is 0.
Okay, which is not physical.
Which is not physically correct.
Okay.
Because that means reflection coefficient we are getting 1.
Okay.
So, and this example is for discretization lambda by 5.
Okay.
So again we are saying that the beam is looking not continuous.
Okay.
But still it is better than the case in lambda by 3.
Okay. Okay.
But still, as when we see our coefficients,
yeah,
the transmittance is 0.
Okay.
We'll see now for lambda by 10. So in this case, you will observe that some part will be transmitted to successive layers, and that will again get reflected from that layer.
Okay. So that's what is happening in this case. So you have something coming, and then it's getting transmitted, and then it's getting reflected from the second layer.
Yes.
Okay.
So it will get transmitted here.
So Mayur, is it possible for you to explain how this physical problem? It's good to see the physics of it, but for us to model this in the finite difference method, can you explain the simulation setup itself?
Yes. We are taking 2 dielectric slabs with permittivity epsilon R1 and epsilon R2.
Okay.
For which we are taking values as 2 and 4 respectively.
Okay.
And then we are injecting a pulse, a Gaussian pulse from this place. And at the other side, we are seeing transmittance using one of the monitors. And on the back side of source, we are seeing reflectance.
Okay. So basically, what you are telling us, this is the source side, and then the source is a Gaussian pulse. Roughly, what frequency you are talking about?
I'm talking about 600 terahertz.
Okay. And then this is the point where it meets the first slab with the relative permittivity of epsilon R1.
Yes.
And then the second slab is epsilon R2, and we can increase the slab by stacking them one over the other.
Exactly.
So then this is the reflection side, and this is the transmission side. So what you're basically modeling is a Maxwell equation, and you have the basic source information. You have the boundary. Do you have any specific boundary conditions you're forcing?
Yes. I am forcing a boundary condition which I can show here, our simulation boundary. So we are truncating our physical domain.
And what kind of boundary condition you're forcing here?
So here I am putting PML on all sides.
Okay, we will focus on the PML later on. For now, it's enough to know that there is a boundary condition that is being forced, and there is an input pulse which is coming, which is a Gaussian pulse, roughly in the 600 terahertz range. So it's in the optical range.
Yes.
And then you have a reflection that is being measured at this point, and then you have a transmission that is measured at this point.
Yes.
And these are basically sensors that you define in the domain itself.
Yes.
And basically, you're solving this using a kind of a tool called numerical. Which is a finite difference solution.
Yes.
Okay. So is it possible that you do the simulation one more time so that we can see the physical aspect of it?
Sure. So this is the setup which you can see. I'll show you by rotating.
Okay.
So this is source.
This
is a Gaussian source. And then this is I'm measuring reflectance here with this monitor. And with this monitor, I'm measuring transmittance. Okay. And this is the FDTD simulation region. This one.
Okay.
So I'm truncating. The slabs are looking bigger than my simulation region because I'm truncating the domain.
So this yellow part is your simulation region.
Yes.
Basically.
Yes.
Okay.
So I will put it on simulation. So we have simulated it. We'll check transmittance and reflectance values.
Yeah.
So as you can see, at this 0.5 micron wavelength, which corresponds to 300 terahertz frequency, the transmittance is of the order of 10 raised to minus 21, which is very less.
Very less.
And we'll check reflectance. It is of the order of 0.78, minus 0.78.
So almost like everything is getting reflected.
Right.
Okay. So if we change the frequency, this order is going to change as if. And it's pretty much reflecting the physics of the reflection. And thanks for explaining us this problem. Mayur, I also know that you have simulated a X-band waveguide, which is roughly 8 to 12 gigahertz in the microwave region. And I've asked you to also simulate this particular problem using the finite difference method. So could you please explain how you have done it?
Yes. So I have taken first, I have simulated three things.
Okay.
So first is a waveguide without any bend, straight waveguide like this. And second one will be a waveguide with elbow.
Okay, so basically you have looked at different kinds of bending. Either you have a rectangular bending like this or a curve like this. So you're trying to see, so what he is trying to do is basically trying to see how much amount of the power that is getting transmitted on the other side and what is the impact of the bend itself.
Well,
so basically
we'll be simulating the modes inside the waveguide.
Okay.
And we'll be seeing the effect of this bending on the power that is transmitted on the output.
Okay, excellent. So can you explain us the problem itself?
So these are the dimensions for our waveguide which we have simulated.
So this is without the bend?
This is without the bend.
Okay, and then
this is the second simulation which we have done.
So you've taken a rectangular perpendicular bending. So it's a classical elbow. And then you have done also a radius of curvature. So basically this is pretty much like curving it like this. And the dimensions are pretty much the dimensions that you have taken it from here.
These dimensions correspond to a maximum wavelength of 3 centimeters.
Okay.
So that corresponds to 10 gigahertz.
Okay. So let's see how the simulation itself is looking for this particular problem and how we have done this using finite difference tool. So this is lambda by 3, which is a pretty much kind of a straight waveguide. And you're trying to send a kind of a Gaussian pulse.
I'm sending a Gaussian pulse and looking inside the modes.
The modes and how it's propagating. So go a little bit finer in the discretization. If you have more lambdas.
This example was for lambda by 3.
So if you have more cells per lambda.
This is for lambda by 5. So we can see that we are able to see the mode little clearly as compared to lambda by 3.
So in the case of lambda by 3, there are not enough grid points to sample the points. So it's not really simulating the real physics. Whereas in lambda by 5, we have enough points per lambda. So we're able to see the wave actually propagating. And obviously there are some errors which might be reduced
in success. So this lambda by 10.
So can you show the lambda by 10?
We can see a clear mode.
So you see a clear propagating mode inside. So can you go higher up? Is there any other lambda by 20 you have done?
Yes, I have done using non-uniform mesh.
So you have done, this is for the uniform mesh, and then you have taken a non-uniform mesh. So that means the rectangular or the cubical grid what you're using is going to be non-uniform. As in there will be small cubes, big cubes, so on and so forth.
At the edges where the boundary conditions are there, it is taking very small discretization, and other places discretization is bigger.
So it's really simulating it in a much more resolved way, so you're able to see clearly the mode propagation. Obviously when you see the comparison of error compared to more fine, you might be able to see what is the actual error that is also coming in these kind of simulations. So now can we see also the bend?
So this is for lambda by 3.
So this is a classical bend, so where you have a kind of a perpendicular bend. And you see that
it is not able to, there is some like perturbance inside and it is not able to properly simulate the mode inside.
So can you go finer in the discretization? So this is lambda by 5. So you're able to see that you're able to get, and there is kind of bit of a reflection. And then once it's getting reflected, there is kind of a perturbation.
This is for lambda by 10.
So you're seeing it much more resolved. You see the mode.
It's a complete Gaussian pulse, we can see.
And you see that it's getting reflected.
Yes.
So it actually acts as a perfect reflector,
Right.
like perfect electric conductor.
Right.
Okay. So then, can you also show us when you have a bend instead of an elbow, a kind of a bend with certain radius of curvature?
This is for lambda by 3 discretization.
So again, here the physics is not replicated properly by the discretization.
Right.
So when you have lambda by 3, whatever you're getting simulated is kind of a noise which is not really clear, and there is so much numerical error.
Yes.
You're not able to
and
resolve.
if you see the profile of this, if we plot electric field versus the distance it is traveling, that profile is very not clear.
Okay.
It's not a Gaussian profile,
Okay.
which we are putting inside.
Exactly. So let's go a little bit finer in the resolution.
So this is for lambda by 5.
Now we are able to see a little bit better, but still there is a bit of resolution issue. So can you go a little bit more finer? So this is the last one you have done.
Yes.
So you have a much resolved, much more clean mode that is propagating.
Yes.
And you see that it's propagating nicely.
Nicely.
So that's
also
kind of a problem that you have done is, you basically a waveguide that is bent and you're trying to simulate it nicely.
Yes.
And you're assuming that this dimension, the Z dimension, is infinitely long. So you're basically simulating as it's a 3D, from a 3D problem to a 2D problem. Excellent. So thanks a lot, Mayur. Thanks for doing this nice simulation on the numerical finite difference solver, and it is quite helpful for the students to know how you can do modeling using finite difference on a commercial solver. Thank you.